Now I will present the introduction. So what is FTIR? Fourier transform infrared spectroscopy is an analytical technique that uses infrared light to study a sample's molecular makeup. Infrared light interacts with the vibrations of atoms within molecules. Different functional groups in molecules absorb specific infrared frequencies. By analyzing the absorbed frequencies, FTIR creates a spectrum like a molecular fingerprint. Imagine light with frequencies beyond what our eyes can see. FTIR uses this infrared light to probe a material. The light interacts with the tiny vibrations of atoms within the molecules, and certain frequencies get absorbed depending on the molecule's structure. By analyzing this absorption pattern, FTIR generates a unique spectrum just like a fingerprint that tells us which molecules are present in the sample. Now I will present about the working principle of FTIR. So first, an infrared light source emits a broad spectrum of infrared radiation. Second, the interferometer splits the light beam and creates an interference pattern. The sample is placed in the light path and specific frequencies are absorbed by its molecules. The detector measures the intensity of the transmitted light after interacting with the sample. A computer analyzes the interference pattern and calculates the final FTIR spectrum. Think of FTIR as a light maze with a special detector. The light goes through twists and turns, and the samples acts like a gatekeeper, absorbing certain frequencies. The detector then measures the remaining light, and a powerful computer translates this information into a spectrum, revealing the identity of the molecules present.
Is methodology. Methodology for FTIR. First is preparation of tissue samples. First is you must have tissue samples. Sample preparation. The tissue samples need to be prepared in a suitable form for FTIR analysis. This can involve A. Thin section. First is tissue samples can be cryo-sections to produce thin discs. B is drying. Samples may need to be dried to remove water. Second is starting the spectrophotometer. First is turn on the FTIR and click on IR solution on the desktop. Third is IR solution starts. 4 is click on measure button. 2.5 is select the measurement menu on the IR solution. 6 is select initialize on the menu. 7 is the PC initiated communication with the FTIR. 8 is to exit the auto adjust process. Click OK. When the status monitors on the right window shows a green color, the system is OK. Community lens and laser. That is acquisition and processing 3.2 spectrum analysis. 3.2.1 is the obtained spectrum is analyzed here for characteristic absorption peaks corresponding to different molecular bonds. Then look in reference spectra to determine which molecular makeup is present in the tissue. 3.3 is interpret result. First is use the data to identify the biochemical composition of facial tissue. It can be applied to understand the existence of the fibers, glands, or additives in the disposable tissue. 4 is print. Click on print form button. Add title in the text box display. Keep the templates open and select the file name. 4 is click on print preview and print your spectrum. Also, you can take a screenshot of your spectrum and print the image. 6 is save. The spectrum should be saved automatically after measurement in the personal folder. Select file button and go to save as. The personal file will be saved as SMF format. This can only be opened with IR solution software. To export the personal data, go to the file menu, select export text ASCIRSDX. 4 is alternatively press the print screen button on, on the keyboard, then open. Pen, pass the image into the blank canvas, crop with the rectangle selection tool, copy and paste into a new blank pen canvas and save to your file. The result of FTIR for tissue. First is the spectrum of a tissue samples. Second is FTIR spectra comparing a tissue samples. Third is spectrum of the tissue sample is compared to all other compounds. Fourth is the spectrum of cellulose. Is the result. The fifth is the spectrum of cellulose overlap with spectra from aliphatic primary amides and aliphatic hydrocarbons. 6 is the transmission characteristics across a range wave number. 7 is the transmission characteristic across a range of wave number. 8 is the fingerprinting of a molecule.
Okay, for the discussion, FTIR analysis of tissue samples reveals valuable insights into biochemical composition. Distinct absorption peaks observed in FTIR spectrum. Peaks at 3,300 cm power of -1 are the single bond of ONH and also single bond of NH stretching vibrations indicating hydroxy and amine groups. Peak at 1,650 cm power of 21, single bond of C and O, stretching vibration characteristic of carbonyl groups in proteins and amides. Peaks between 2,800 and until 3,000 cm power of 91. Carbon and hydrogen stretching vibrations confirming presence of aliphatic hydrocarbons. Comparison with reference spectra supports identification of molecular components. Tissue spectrum closely resembles cellulose, indicating it as a major component. Coexistence of cellulose, aliphatic primary amides, and hydrocarbons confirmed in tissue sample. Transmission characteristics across wave numbers show varying absorption intensities of molecular bonds. Molecular fingerprinting aids in precise identification of tissue's biochemical composition. FTIR analysis is a powerful tool for detailed molecular composition. Now I will share about the applications of FTIR analysis. In polymer science, FTIR helps identify polymer types and analyze their functional groups. Second, the forensic scientists utilize FTIR to identify unknown materials at crime scenes. Third, pharmaceutical companies use FTIR for quality control and ensuring the purity of drugs. Now,
the FTIR analysis of the tissue sample provides comprehensive insight into its biochemical composition. The spectrum reveals distinct absorption peaks, including prominent signals at 3,300 cm power -1, OH and NH stretching, and 150 cm power -1, CO, CH stretching, CO stretching, and 2,800 until 300 cm power -1, CH stretching. This finding indicates the presence of hydroxyl and amine groups, carbohyl groups typical of proteins and amides, and aliphatic hydrocarbons within line tissue. Comparison with reference spectra confirm cellulose as a major component alongside aliphatic primary amides and hydrocarbons. The overlapping spectral regions provides further evidence of the tissue's composite nature, reflecting diverse molecular bonds and functional groups. The molecular fingerprinting analysis highlighted the unique spectral features that facilitate precise identification of the tissue's biochemical makeup. This underscores the utility of FTIR spectroscopy as a powerful tool for detailed molecular profiling of complex material like tissue, offering valuable insights into their chemical composition and structural characteristics. Just that, thank you.